Okay, hello everyone. I just started the recording and I have some announcements here. Let's see, I see we have the chat window. A question on the midterm. Yes, we do have a question on some midterm logistics. Okay, so midterm logistics. Okay, so the question, here's the situation for the midterm. We're going to do a 2-hour block in the morning and a 2-hour block in the evening. Okay. However, if you would like to take it at a different time, you can do so. The problem is we cannot guarantee immediate answers to your email questions. So let me summarize that here. Okay, so what we have here, you see there's a 2-hour block in the morning. There's a 2-hour block in the evening. So it's in some sense, it is recommended that you take the exam either during this time or during this time. Okay. If you do so, then we can guarantee quick response to your email questions. We recommend that you email your questions. Okay. If you would like to do a different time on Friday, you can do so, and we will attempt to answer your questions as quickly as possible, but we won't be staring at the computer screen the same way. We will be here during this 2-hour block in the morning and a 2-hour block in the evening. You could even get creative. You could start at 8:30 in the morning and finish at 10:30. Sure, you can do that. That's another example of the freedom that you have, with the understanding that quick email response is available during these 2-hour blocks, right? A 2-hour block in the morning, 2-hour. Yep. And so again, we got the B courses timer. And so the current homework assignment, as you know, one portion is basically a dry run here using a B courses timer together with preparing a PDF and a file upload. Yeah, great question there in the chat window. So, and I'll just write it out. Other times, okay. Quick email response not guaranteed. To your questions. Oh, brother. I get so confused on how you spell. I just have to make a mess of it. Sorry, I forgot how you spell guarantee. So other announcements here, reading assignment. So here's what we're doing. By the end of this week, we're going to finish chapter 11. And as you know, once you finish chapter 11, this is a major milestone in the book. Then you have some freedom to explore the following chapters in whatever order you like. We're going to go straight to chapter 13. And then later in the course, we'll revisit chapter 12. We'll come back and do chapter 12. The reason is chapter 12 is not so appropriate for the final exam. But chapter 13, there's good stuff here with the Hamiltonian formulation of mechanics. This is perfect for the final exam. So by doing chapter 13 before we do chapter 12, we'll be perfectly positioned for the final exam. So homework 9 will be due the Tuesday after the midterm. And then these are my office hours this week. It's understood every one of these is a 1-hour block. And of course, the exam's on Friday. Okay, so those are the announcements. Let's now return. We have some fascinating topics in rigid body motion. And in order to really help understand this, I have prepared, I made this for you. Okay, what is this? It's so in the garden, we have these trees that drop these things, but they're basically impossible to eat. They taste terrible, so they're perfect for physics experiments. So in the homework assignment, I mentioned a well-known problem called Feynman's plate. It's the problem of the free motion of a rigid body with two moments of inertia that are equal, okay? And so I've labeled these three unit vectors. We talked last time, in cases such as this, where lambda 1 is equal to lambda 2, you must arbitrarily choose an E1 hat, and it is attached to the body, okay? That's why I made this model, to emphasize these unit vectors should be thought of as massless. Let's assume these are massless twigs here, massless and connected to the body. There's E hat 2 and E hat 3, very important to us. This thing has a symmetry axis. It's similar to a plate. Like here's a plate. This is a plate, right? They have the same structure in the sense that there's a principal axis of symmetry. In this case, the largest moment of inertia is lambda 3, right? And we've talked about that. It's the largest moment of inertia because you have the mass distribution as far away from the axis as possible. Lambda 1 and lambda 2, the eigenvalues that go with these unit vectors, the eigenvectors, they're smaller because if you spin it about this axis E1, for example, the mass distribution is a bit closer to the axis of rotation. Okay, so let's take a second to compare this to the picture that's in the book. Okay, so here we have our wonderful textbook, and we have this very useful picture. Notice the keyword egg, okay? You can talk about an egg or a plate. Those are some keywords that I just mentioned. Alternatively, you can talk about prolate spheroids and oblate spheroids. We've talked about the oblateness of the Earth, right? The oblateness of the Earth is caused by the fact that the Earth is spinning on its axis, and we worked out the equipotential. It causes an equatorial bulge that goes all the way around the planet. That's because of the spinning on its axis, not to be confused with bulges caused by tidal forces. That was a different topic. That was a prolate spheroid. The tidal forces caused a spherical distribution of water to become a prolate spheroid. And if you have water spinning about an axis of symmetry, such as our water planet, then you have an oblate spheroid. So here it's useful to use terms that are kind of easier to remember. Egg-shaped, okay? So this is an object, notice E hat 3. It's very important to us that the number 3 axis, this eigendirection E hat 3, this is the one that has a moment of inertia that's different than the other two. E hat 1 and E hat 2 are perpendicular to this axis. They're not shown in this picture, but they have, in this picture, they have a larger moment of inertia, okay? The extreme example would be to use a pencil or a pen. That's right, you heard right. Rather than an egg, we could use a pencil or a pen. That would really make it clear that the moment of inertia for the number 3 axis is much smaller than the other two. For axis number 1 and number 2, you would be spinning it like so, a lot more angular momentum for the same angular velocity. Okay, so to emphasize this picture in the book, and what I want to emphasize here is the capital omega B. It's hard to see, I think, because I'm a little too close to the camera, but that's a capital omega sub B. All right, and notice the sense of rotation is drawn on here, and that's correct for the egg. Okay, on the previous page, you know, we have some nice results. The symbol omega B is defined here. It's important to understand this formula is valid both for the case where omega B is positive and where it's negative. If lambda 1 is greater than lambda 3, then omega B is positive. Okay, that was what we saw here. Remember what we said. For this picture, in the extreme case would be a pencil or a pen rather than an egg. Lambda 3 is small compared to lambda 1 and lambda 2. Lambda 3 is small. Of course, they're all positive. All the lambdas are positive. So for this picture, lambda 3 is smaller And consequently, capital omega b is positive. Okay. All of this discussion goes through for the opposite extreme. That's the dinner plate. Okay, a circular plate. You could also throw a coin into the air. Then lambda 3 is larger, as we just discussed, for that piece of fruit, that inedible fruit. You have lambda 3 larger. Omega b is negative. Okay, so in this diagram, the sense of circulation in this picture goes the other way. Remember, this picture on the left shows you the situation in the body frame. In the space frame, they always go this way, okay? Regardless of the case of the egg or the plate, the sense of rotation in the space frame is shown by this little arrow. It's a loopy arrow showing you that we have precession about L, the angular momentum, which is fixed in the space frame. What is different, remember these pictures are drawn for the egg. And notice the omega vector is between L and E3. If you do the plate, then L is still fixed in the laboratory frame, in the space frame, and these are still coplanar, but the roles are reversed here. In other words, the omega vector is outside. Okay, so let's go through this. I want to say a few more remarks, and we'll have a discussion here. Again, we have this wonderful piece of fruit with the 3 unit vectors. First, let us explain using tensor analysis. Let us explain why I was justified in sticking these twigs into the piece of fruit. Okay, if this were edible fruit, I probably would not have taken twigs out of the garden, right? Because I would be bound to eat this thing after lecture. All right, but let's stay on topic here with the physics. Okay, so tensor analysis. Remember our most fundamental equation here. Okay, we're going to revisit this fundamental equation, and we're going to understand from the point of view of tensor analysis why I was justified in inserting these twigs into the fruit. That is to say, why is it true that the E hat 1, E hat 2, and E hat 3 unit vectors, why do they move with the rigid body? We can explain that using tensor analysis. All right, remember, if you have an eigenvector, okay, remember the situation. This equation, which I put in a box, this is always true. If you have an eigenvector, then something very special is true. Okay, so this is a very special state of affairs. The angular momentum is parallel to the eigenvector. Okay, now let's use our knowledge of tensor analysis for an arbitrary rotation matrix. It could be a rotation about the z-axis or a rotation about any axis. For an arbitrary rotation matrix, we can left multiply by r. So here, this r rotation matrix. Remember, a matrix is an array of numbers. It's a representation of a rotation operator once you have chosen a basis. So using the space frame as our initial choice of axes, we can use a 3x3 matrix to describe a rotation. And we've written out some formulas for this. We have the so-called direction cosines, etc. So now this R is a rotation matrix. If this is true here, L equals lambda times omega, then we can left multiply by R. It'll still be true. We have not yet done anything really amazing, but the next step will be clear. Okay, I'm left multiplying by this rotation matrix. Scalar multiplication commutes, right? So with matrix multiplication. Okay, so far so good. But let's also investigate what happens here. And here the crucial thing is we're going to left multiply by the rotation matrix, and in between, you see this is a matrix product. You have a 3 by 3 matrix times a column vector. In between those two factors, we can insert a resolution of the identity. In other words, we're certainly welcome to put the 3 by 3 identity matrix there. There's no change there. And then we can write that matrix as a rotation matrix times its inverse. Okay, so again, I've left multiplied by this rotation matrix. Okay, there, again, the tilde, that is our notation for the transpose. And of course, the associativity of matrix multiplication. Okay, the associativity of matrix multiplication, very important to us here. So that means as long as you preserve the order, you are welcome to evaluate matrix products in any sequence that you like. So if we first evaluate this product, the transpose of the rotation matrix times the rotation matrix, something wonderful happens. The product of those two matrices is the identity matrix. Okay, the identity matrix times omega is once again omega. So you can see we recover this stuff here. So what we've done here is certainly valid. We've inserted a resolution of the identity like so. But now let's incorporate some parentheses in a slightly different manner. Okay. So I did put in some parentheses. And again, if you look at the course catalog description of Physics 105, we are supposed to talk about tensor analysis. So this is a good opportunity to talk about it. Again, tensor analysis is not appropriate for the final exam or the midterm. So don't worry about it in that sense. But we'll be talking about these topics. Also, as you know, some of the material in this chapter, the last couple of sections in chapter 10 are not appropriate for the exams. And I will, for the final exam, I will prepare a document telling you that the last couple of sections in chapter 10 are not appropriate for the exam. They will not be on the exam. No need to make those remarks for the midterm because you know the midterm just goes up to the first part of chapter 10. So the end of chapter 10 is not relevant for the midterm. What we've shown here is if you have a rigid object, okay, if you rotate the rigid object, then the eigenvectors rotate along with the rigid object. So all of these remarks here concerning tensor analysis, we can summarize. We can summarize this verbally in English, the eigenvectors. Okay, so in summary, the eigenvectors rotate with the rigid body, right? In principle, if you have a rigid body such as this thing here, we have a prescription how to compute the inertia tensor. So if you rotate this rigid body, then we have a clear prescription for how to compute the inertia tensor. You could do that. You could then, having computed that tensor, you could look for eigenvectors and you will find them, okay? And once again, you could solve for the eigenvalue, you could solve the eigenvalue-eigenvector problem, okay? What you will find is that the eigenvectors of this new problem are simply the rotated versions of the original ones, and the eigenvalues are identical. That's what we've proven here with this choice of parentheses, right? The idea is if omega is an eigenvector, so if this statement is true, then we've shown that this rotation matrix times omega is an eigenvector of this. You recognize this as the transformed. Remember, the inertia tensor is a rank 2 tensor. Rank 2 tensors are nice because the transformation law can be written using standard matrix multiplication. You just need to put this transpose here. Remember, for rotation matrices, the transpose is the inverse, but quite generally you just have the transpose here. Okay, great. So what we've done here is we have shown that if you rotate a rigid body, okay, if you rotate a rigid body throughout its motion, it's always true that the eigenvectors, if you identified some eigenvectors in its original position, those eigenvectors just rotate along with the body. Okay, and that's why I was justified in sticking these twigs into the piece of inedible fruit. All right, so let's talk about how this relates to some rather difficult problems that we've been studying. Okay, recently we talked about the case of a coin rolling on the table. Okay, let's remember, we did this recently. And of course, last week on the 22nd, I drew this picture. Now these red arrows, so the red arrows in this picture, they become these twigs. And I'm holding it now in approximately the same, right? You see the E hat 1, there it is. E hat 1, red ink. Okay, so this is the picture to have in mind here. All right. Okay, so the case of the coin rolling on the table is something we discussed. Ay, caramba. Looks like that piece of paper is gone missing. What we can do here, most likely I displayed these drawings here. So we had this problem, the coin rolling on the table, and in our last meeting, we didn't get to finish this discussion. Okay, the crucial observation here in terms of foundation skills is that if you have a coin rolling in a circular path like this, and what does that mean? We're assuming that the system has been prepared so that it rolls in such a manner that the center of mass of the coin executes uniform circular motion. If you launch a coin with an arbitrary initial angular velocity, that may or may not be true. It can actually go into some more complicated motion. This is a special state of affairs. You've carefully crafted it. And what's the key? The initial angular velocity, right? Here's this instantaneous axis of rotation. And we identified that last time by arguing that the point of contact, since we have no slip rolling, and we've identified this point of contact, the mass distribution has the property that at this location it's motionless. So then you know that this point must be a point on the instantaneous axis of rotation. Furthermore, we attached a styrofoam rod to the center of the coin, similar to those twigs I showed earlier in the piece of fruit. Okay, it's styrofoam. It does not affect the moment of inertia tensor of the coin, but it's part of the rigid object, and we've identified that this end of the styrofoam is motionless. So now we have 2 points on the rigid object that are motionless. That's enough to fully define this as the instantaneous axis of rotation. Okay, so once you've defined the instantaneous axis of rotation, there are some more calculations to be done. What we'd like to do today is appreciate how to compute the angular momentum. In this case, the angular momentum in the laboratory frame, in the space frame, it's not constant. The reason is we have torques on the system. Okay. That's in contrast to the other problem we're going to talk about, Feynman's dinner plate, this famous problem of Feynman's dinner plate. That's the case of a free rigid object. There are no forces. You can do this on in a zero-G environment. There would be no forces. In the cafeteria where Feynman first noticed this phenomenon, of course, gravity was acting on the plate. There was some center of mass motion, but that's logically distinct because it's a uniform gravitational field. Right, we approximate it as a uniform gravitational field. It exerts no torque on the plate. If you're in a non-uniform field, there can be a torque. But for a uniform gravitational field, the center of mass motion separates out because there are no torques on the system. So this experiment of throwing a dinner plate into the air and catching it without dropping it is an experiment you can do, and you can observe this wobble, right? The dinner plate wobbles, and the remarkable thing is you can observe clearly, especially if you have a fortunate choice of interior lighting. If the light sources inside the room are such that reflections off the plate, off the surface of the plate, are easy to register in your eye, then you can easily see that the normal vector to the plate precesses with one angular frequency, and the large red medallion, the Cornell cafeteria medallion, which was printed on the plate, that can be seen to rotate at a different angular velocity. So this was very visible when that random person threw the plate into the air. Okay. So let's make some closing remarks on this rolling coin problem. The overarching theme throughout all these problems is understanding how to compute the angular momentum from the angular velocity vector using the moment of inertia tensor. So in this problem, we identified, under the assumption that this had been prepared in such a way that the center of mass executed uniform circular motion, and of course, the point of contact traced out a circular path with a larger radius because the coin is leaning. We identified the instantaneous axis of rotation. Surprisingly, it's as shown in this picture here. And if you want to draw an omega vector, a great place to draw it would be rooted at the origin. Here's the capital cursive O for the origin. The omega vector at the instant this picture is drawn, the omega vector of this coin points like so. Okay. There are geometrical parameters, so you can start talking about the angles. We won't go through all the angles in this lecture today, but let's appreciate that you can identify this angular velocity vector, right? And of course, this problem is too difficult for an exam problem. This is more of a problem you spend some hours thinking about. Now, this omega vector can be written as a sum of two vectors. Okay, this is the crucial observation. And using these dotted lines, I indicated you can write this vector as a sum of two contributions. One contribution, which is parallel to the surface of the coin. The other contribution, I'm indicating with a pen, is parallel to the axis of symmetry. This is a wonderful thing to do because you want to multiply the inertia tensor times omega to get the angular momentum. Well, omega is written now as a sum of two contributions, and the inertia tensor times this contribution here, that's lambda 1 times that omega contribution. And the inertia tensor times this contribution here, that's lambda 3, right? We like to use lambda 3 for the eigenvalue associated with the symmetry axis. Okay, so the takeaway message for this problem, the main message is crucial to understand the instantaneous axis of rotation. Once you have your omega vector, here it is, this lowercase omega vector, you can write it as the sum of two vectors. One, so these are two vectors that kind of respect the structure of the inertia tensor. One vector is in the plane perpendicular to the axis of symmetry. So we know the eigenvalue for that one. We must multiply that contribution by lambda 1, which is equal to lambda 2. This component, this contribution to omega, this is a vector that's parallel to the axis of symmetry. So we multiply that by lambda 3. So in doing this, you compute the angular momentum. Okay, again, for this problem, the angular momentum sweeps out a cone. The angular momentum in the space frame, also called the laboratory frame, it sweeps out a cone. I have to be careful not to hit the document camera. Right? So both the angular velocity vector and the angular momentum vector, they sweep out cones. And again, in this case, L in the space frame is not constant because there are torques. Okay, so that is a conclusion. Those are closing remarks on this problem of the coin rolling in a circle. A special case, you've probably seen this towards the end. If you do this in real life, there are frictional losses, right? Dissipation, you got air resistance, sound waves, etc. There's a case where the coin starts to get very close to the table. The center of mass is getting closer and closer to the table. It makes a distinctive noise. It's going very quickly. The point of contact is zooming around very quickly. So again, the point of contact moving very quickly around this circle at that later stage of the game, but the molecules in the coin are not moving that quickly. They individually move up and down and they circulate a bit. So those are some interesting special cases for this problem. All right, so now let's return to this issue of the dinner plate. All right. And what we want to do here is appreciate that the presentation in chapter 10 basically is a two-stage approach. So we can describe this quite generally like this. The first thing we do, we solve Euler's equations. All right. If you solve Euler's equations, you can get a solution for omega in the body frame. Okay. And I've emphasized here, what you have is a solution for the omega vector as a function of time relative to the body frame. Okay, let's talk about an equivalent way to say this. If you're talking about omega as a function of time in the body frame, that is fully equivalent to saying okay, because remember, this is our notation, omega 1, this is the dot product of E hat 1. There's E hat 1. With the omega vector, omega 2 is the dot product E hat 2 with omega, etc. So Euler's equations, of course, give you a system of first order differential equations to get these omegas. They are first order if the torques are 0. What if the torques are not 0? Then life is more complicated because we have to talk about step 2. Remember, all of this was essentially step 1. Step 2, all right, the answer here is we have not yet solved the problem because our goal in physics is to find the classical state of the system as a function of time. So we haven't really solved this problem until we can state how the orientation of the body in the laboratory frame changes as a function of time. Let's talk about step 2. Okay, so here's step 2. We must reconstruct the motion. Okay. And so we saw this for the free rigid body with the case of 2 equal principal eigenvalues. So lambda 1 equals lambda 2. We could solve for the omega vector in the body frame rather easily. The omega vector in the body frame, it precesses around, and we have a nice formula for that. Step 2, we must reconstruct the motion in the space frame. This can be more difficult, but let's appreciate our friends across the street, so to speak. We got the various physics buildings. Across the street, we have Evans Hall with all these mathematicians, right? And there were several decades recently, let's say 70s, 80s, 90s, where they made a lot of progress on this general notion of using symmetries and the so-called theory of reduction. Well, you arrive at a reduced problem and you solve that. So when you solve for omega in the body frame, wonderful, but what does that tell you about the space frame? You're still a far cry from solving the problem in the space frame. And so let's talk about what is required to solve for the motion in the space frame. So for example, there are the Euler angles. Okay. So this is kind of the big picture. We're interested in solving for the motion of a rigid body, right? We've studied step 1 intensively with the Euler equations. And yes, you can solve and get omega 1 as a function of time, etc., omega 2. Now, the Euler angles. Let's have a look at the Euler angles. So what's happening here? We have this section 10.9. Notice the asterisks. This particular section will not be on the final exam, but nevertheless, it's useful for us to talk about this. All right. And the Euler angles are a system of 3 angles. I understand it's hard to see. And again, that's in harmony with what I said earlier. Just kind of enjoy the discussion. Don't worry about the details too much. The important thing is that there are 3 angles. Here's this angle phi, here's this angle theta, and here's this angle psi. Okay. Notice that theta and phi end up being the familiar polar coordinates, right? We've often talked about spherical coordinates. They're the polar coordinates of E hat 3. Okay. So there's a sequence of constructions here. These 3 sequences in the book are one way. I should say this sequence of 3 images shown here in the book. This is one way to define Euler's angles. So you start by a rotation about the z-axis. The angle of rotation is phi. That gives you these 2 new unit vectors here. Then imagine taking this disk here and tilting it. This angle theta tells you we're going to rotate, pointing straight up. Here's z hat pointing straight up. We're going to rotate this angle backwards. Now we've got this E hat 3. When we write this by hand, we write E hat 3. And it's inclined at an angle. So this disk is now tilted. And now in that tilted disk, we have a rotation. You see this angle psi. So it's a sequence of 3 rotations. It's important to understand you can describe this sequence, right? This is one way to describe the sequence. You can describe this in another manner. So let's make a quick remark here on Euler's angles. Okay. Again, these Euler angles, it is an optional remark from the point of view of the final exam and the homework. We won't be doing this stuff on the homework, but let's observe that we have a product of 3 rotations. Okay, what I have done here, I've written 3 rotation matrices, a product of 3 rotation matrices. The notation is as follows. This is a rotation about the z-axis. That's the laboratory z-axis, the space frame. And we rotate about an angle phi. As always, we use the right-hand rule to determine the positive sense of rotation. Then we rotate about, so after doing that rotation, then we rotate the system again about the laboratory y-axis about an angle theta. And then we rotate about the laboratory z-axis by an angle phi. So it's important to understand, just as in quantum mechanics, if you have a sequence of operators, this is a product of operators, you must imagine them operating, you must imagine this product operating on something over here to the right. This could be any one of the position vectors of particles inside the rigid object, okay? But quite generally, when we talk about this product of operators, you can think of this product operating on some vector over here on the right. And you first operate with this factor on the right because it's right here next to the vector. Again, this is the associativity of matrix multiplication. You put parentheses around this rotation operator and the vector, it's some position vector that you're going to operate on. After you evaluate that, then you apply this rotation matrix here. After you evaluate that, then you apply this rotation matrix here. So this is true quite generally for operators, and you've seen this in quantum mechanics. if you write a product like this, we typically write it left to right, but it's understood when this is applied to a vector, the prescription is as follows. First, apply this rotation about the z-axis, then apply this rotation about the y-axis, and then apply this rotation about the z-axis. Notice this three-stage process does not give you this picture here. This picture is a different way of describing it. The final picture, this third one called figure 1010C. Figure 1010C is achieved after you apply these three rotations. After you complete the program here and apply all three rotations, then you have a picture that's identical to figure 1010C. Okay, but notice in that figure we looked at, that's figure 1010. There are rotations about these intermediate axes that have funny names like E2 prime and stuff like that. Okay, not true here. Every rotation here is about a laboratory axis. And you can convince yourself just by drawing pictures that, I mean, I can show you some pictures, but these are kind of rough sketches. So here's some pictures. Okay, so this is the result, the sequence of the three operations. Again, this final diagram is identical to figure 1010C. But notice the philosophy here is first we do a rotation about the laboratory z-axis, then we do a rotation about the laboratory y-axis, and then we do a rotation about the laboratory z-axis. The final answer here is the same as figure 1010C, but these first two pictures are not the same as figure 1010A and 1010B. Okay, so the point of this discussion, we don't want to get bogged down in the details of the Euler angles. Okay, that gets rather technical. Let's appreciate that these three numbers tell you the classical state. Okay, these three numbers there are three angles that tell you the classical state. And this is just an agreed upon convention. The definition of Euler angles is an agreed upon convention for establishing a means whereby you can specify the classical state of the rigid object using three angles. So classical, I should say configuration. Yeah, I misspoke when I said classical state. The classical configuration, that's the instantaneous orientational position of the body, is specified by these three numbers. These three, together with their time derivatives, would tell you the classical state, right? The initial position, the initial velocity. So step two, if you like to use the Euler angles, your goal is to find phi as a function of t, theta as a function of t. Okay. Once you have achieved this goal, then you are living the dream. You've achieved what physicists all over the globe strive to do, which is you have solved for the classical configuration as a function of time. You have solved for the time evolution of the system in the laboratory frame. Notice when you've got these formulas for omega 1, omega 2, and omega 3 as a function of time, you have not done that. You have figured out that the omega vector is precessing in the body frame, but you have not fully solved the problem. Now this is not covered in Taylor, right? Which is okay. Let's just be clear that we have not fully solved it. There are some remarks. For example, for the case of the this problem, we do love this problem, right? The case of a free rigid body with two principal eigenvalues that are equal, lambda 1 equals lambda 2. Here's the picture. Here we have the space frame, and we do have this capital omega S. This is our first inkling as to the story in the space frame, and there's an interesting formula here that omega S is, this is a remarkable formula. It requires quite some effort to prove that, okay? So even when you have this, you're still not done. When you have figured out this capital omega S, then yes, you have solved for E3 as a function of time, because you know E3 precesses steadily about this fixed vector in the laboratory frame. So at this point, when you figure out the capital omega s, you have solved for E3 as a function of time. There remains the question of E hat 1 and E hat 2. We know they're always in the plane perpendicular to E3, but we don't know. There's going to be some, essentially an angular degree of freedom that must be solved for. So once you do that, then you've fully solved the problem. The solution is remarkably simple. Let me tell you the solution. Again, this is for the case of the free rigid body. This theta is a constant. This is something we already knew. Okay. Now phi, remarkably, it grows linearly. It's omega s t. Okay, psi is omega b. All right. So this is for the case, again, I'll emphasize the free rigid body with two moments of inertia that are equal. Okay. So again, this is not presented in Taylor. You can prove it, right? Remember, this section on Euler Angles has some rather technical results. In particular, once you have this wonderful convention for how you define the orientational position of a rigid object using these three angles, then you can ask the question, well, if I know the angles and their time derivatives, what's the angular velocity vector? It ends up getting technical, rather difficult. But some good news is, for the case of lambda 1 equals lambda 2, we can make a powerful statement. We can essentially arrive at a decomposition of the angular velocity vector. Again, two components, one summand along the axis of symmetry, the other one perpendicular to it. And then, because of this assumption that lambda 1 is equal to lambda 2, we have a two-dimensional eigenspace. And the upshot is we can work out the angular momentum of the rigid object under this assumption quite easily. Okay, so you can prove using this, I'm telling you the solution here for the free rigid body with lambda 1 equals lambda 2. This is sometimes called the symmetric top. And yeah, so this is kind of the ultimate goal, right, is to reconstruct the motion. And of course, we're studying this this step 2 also on the homework, reconstructing the motion. On the homework, we're doing kind of a different perspective on it. All right, so the takeaway message then, as we make concluding remarks here on chapter 10, is you can fully solve for the problem, right, in the laboratory, in the laboratory frame, also called the space frame. So let me emphasize that here. Okay. And so let's make some remarks on Feynman's dinner plate. Again, somebody took a dinner plate, they threw it into the air. It was spinning nearly about its axis of symmetry. If you take a plate and throw it into the air, spinning exactly about the axis of symmetry, then you've done something wonderful, right? It's very difficult to do that. The plate will spin, and the central axis of symmetry will just be pointing in a constant direction, okay? But if there's a slight error, you're gonna see this wobble, okay? And conditions were such that Feynman could see the plate was wobbling. That is to say, the normal vectors of the plate had a certain angular, it was sweeping on a cone at a certain rate. And the medallion printed on the surface of the plate was rotating at a different rate. And there was a certain ratio, a certain factor of 2. Okay, you can prove that result using this here. We won't do it in lecture today. Again, it gets a little technical, but the point to appreciate here is that this is the actual solution, step 2. And again, step 2 is not really emphasized in Taylor's book. We mainly emphasize step 1. Occasionally, we do make remarks on step 2. And this existence of capital omega S is a remark having to do with step 2. Okay. All right. Yep, so it's a wonderful story. Again, this stuff was solved a couple hundred years ago. It's really great that Feynman rediscovered the problem and he was very enthusiastic about solving it his own way, right? And as you know, ultimately, Nobel Prize for quantum electrodynamics, one of the most remarkable things coming out of 20th century physics, right? Predicting the anomalous G factor of the electron to 12 digits. Amazing, absolutely amazing stuff. Okay. So we're going to move into chapter 11. Okay. We like working with matrices, and chapter 11 will continue to be a wonderful playground here as we work with matrices. Okay. Now remember something we talked about earlier today. You can use a matrix to describe a rotation, right? It's important to remember a matrix is just a rectangular array of numbers. Okay. The rotation operator, that's an operator, and you can describe it verbally or using other means, but to describe a rotation with an array of numbers, you have to have a basis. Okay, so typically we start by talking about our laboratory frame. We have x hat, y hat, and z hat. That would be the basis for a perfectly valid discussion of rotations, etc. And then these equations told us how to transform these statements to a different frame. Okay. Now in chapter 11, we're going to use matrices. We're going to continue to use matrices. We will have some interesting eigenvalue problems. And we will have what Taylor calls the generalized eigenvalue problem. Okay. It's possible to reduce this to a usual eigenvalue problem, but sometimes Taylor's notion of the generalized eigenvalue problem is useful, and it saves you a little bit of matrix multiplication. Okay, so in chapter 11, we're going to use matrices not only for operators such as rotations, but also for bilinear forms, such as the kinetic energy, okay, and the potential energy. If you are near an equilibrium, if you have an arbitrary system near equilibrium, okay, then let's talk about the potential energy as a function of any coordinates you choose. Remember, in Lagrangian mechanics, you have the freedom to choose coordinates any way you like. And we use the symbol q, right, the lowercase q's. We have all these lowercase q's. Well, if you have a system at a location that's in equilibrium, then we know that the first derivatives of the potential with respect to the q's, they vanish, right? Because those, if they were not vanishing, you would have a force on the system. It would not be in equilibrium. The second derivatives, in general, will be non-zero, and they tell you about the stability or lack of stability. So we're very interested in doing a Taylor series expansion of the potential energy of a system about an equilibrium point, going to second order. And once again, there's a formula for a scalar, the potential energy, which now is a second order polynomial in the small excursions away from equilibrium. And this can be described by a bilinear form. This is an occurrence of a matrix that is not the same as a rotation matrix. So just remember, the matrices are our friends, and they're here to help us. And we're going to solve some very interesting problems using this generalized eigenvalue problem. Okay. So let's, what I just stated verbally, let's go into this in some more detail. Okay. So we'll be talking about quadratic forms. Okay. We have the general idea. Let me put it, oops, I'll put it like this. Matrices can be described, can be used to describe linear operators. And if you have had quantum mechanics, you've seen a lot of this in quantum mechanics, right? So we have linear operators in mechanics. Absolutely, we do have linear operators. Nice example here. Here's an excellent formula. There's a matrix here, this moment of inertia tensor. It's a linear operator. And let's remember the context. Let's do the calculation in the space frame. When we first introduced the inertia tensor, we did the calculation in the space frame. Later, we talked about diagonalizing, etc. But let's continue to talk about the space frame here for a moment. There's a linear relationship. Remember, we worked this out in detail. We used the back cab rule. We figured out all 9 of the coordinates here, all 9 of the components in this matrix. And so the idea is if you have some sort of mass distribution in the laboratory frame, you compute this inertia tensor. Then if you have any sort of angular velocity vector, that is to say, if you choose to rotate this mass distribution about an axis as described by this angular velocity vector, then talking just about that first instant, while the position of the object is still equal to the initial position, but we know that position and velocity are 2 different concepts. So we're having a discussion here where the position, right, the configuration, the classical configuration is still that initial configuration, and we have some velocity, right? Each of the molecules in the object has its own velocity vector as given by the useful relation together with this omega vector. Then you have an angular momentum vector, okay? And so it was this linear relationship, right? This was at the heart of this relation, this formula when we first derived it in the space frame. So this is an example of a linear operator, okay? Matrices are also used to describe quadratic forms. Okay, so let's talk about quadratic forms. We have a couple of nice examples here. The potential energy, if you're near equilibrium, okay. And what have we done here? Well, in chapter 11, we're going to again be using the ideas of generalized coordinates. We will be using Lagrangian mechanics, right? This is going to be a lot of fun. We haven't really done a lot of Lagrangian mechanics recently. Well, chapter 11 is a wonderful playground for us now with the Lagrangian mechanics. We're going to think of an arbitrary system, okay? A typical system might be something we'll do on a homework problem. If you take a rigid rod, let's pretend this pen is a rigid rod, and you attach a piece of string to both ends and you suspend it, okay? Then you can talk about the oscillations of this pen suspended by 2 pieces of string, okay, about its equilibrium configuration, okay? 3 degree of freedom problem. The idea here with the Q's is you have great freedom in how you want to introduce coordinates. Remember, you get to choose coordinates, generalized coordinates. The only rule you have to follow is that if someone has your prescription for how coordinates describe the configuration of the system, then you cannot have more coordinates that are necessary. So for the case of this pen, suspended by 2 pieces of string, 1 piece of string attached here, 1 piece of string attached here, then one way you could introduce coordinates is, well, there's a piece of string attached to this end of the pen going up to the ceiling, okay? You can use 2 angles up there at the ceiling to indicate the direction of that string. That would then define this end of the pen. Then there's a single remaining degree of freedom for how the other end of the pen, which is also attached to the ceiling by a piece of string, its location in space. So again, you have some freedom, and we'll talk about different ways you can introduce coordinates. When we say Q, we're thinking of a very general approach. You have the freedom to introduce Q's any way you like. And here we have assembled the Q's into a Q vector. So for a 3 degree of freedom problem, you have a Q1, a Q2, and a Q3. And this is the transpose. Again, we use the tilde to indicate transpose. This is matrix multiplication. Let's draw a picture of the matrix multiplication. So this is really more of a diagram. Well, this K is a square matrix. Okay. The Q is a column vector. And the transpose of Q is a row vector. And this is a perfectly well-defined matrix product. Let's be very clear on what we're doing here. This is an n by n matrix. Remember, this Q vector embodies our coordinates, and we like to use Q1 going all the way up to Q lowercase n. All right. So when you see that Q vector, it's a column vector. You've got Q1 here and Qn down here. Okay. So this is a matrix. It's an n by 1 matrix. And this is a matrix. Again, you've got the transpose of that. So here's Q1 all the way up to Qn. And this is a matrix. It's a 1 by n matrix. Again, there's the convention that when you describe the dimensions of a matrix, first you indicate the number of rows, 1 row. Then you indicate the number of columns, n columns. Same is true here. So we have a product. It's a 1 by n matrix times an n by n matrix times an n by 1 matrix. This equals a 1 by 1 matrix it's a single number. It's a scalar. The potential energy of the system is a single number. It's a scalar. This is a 1 by 1 matrix. Okay. And again, these are the standard rules for matrix multiplication. Think back to Physics 89 and or Math 54. Okay. Matrix multiplication. If you're going to multiply two matrices, then the number of columns in this matrix has to equal the number of rows in this matrix. N equals n. Works out perfectly. Okay. Here, the same rules for matrix multiplication would be saying you're going to be forming dot products. You take this row vector, you form dot products. Okay. Again, we have the associativity of matrix multiplication. If you like, you can first multiply this 1 by n matrix times the n by n matrix. In doing that, you will be forming dot products with the columns of this matrix dotted into this row. Okay. The resulting object is a row matrix, a 1 by n matrix, and then you can easily form the matrix product with this column vector, an n by 1 matrix. That's just a familiar dot product giving you the single number. Alternatively, you can first multiply the n by n matrix times this n by 1 matrix. That again gives you a column vector, an n by 1 matrix. And then you can easily multiply this row vector times the column vector. That's a dot product. So again, the associativity of matrix multiplication, we have that working for us here. The important thing now is this potential energy is 1 by 1 matrix. That's just a single number, U, and it's measured in joules. Right? Very similar structure here for the kinetic energy. And this is something we investigated way back when. We showed, all right, at that time we used capital A for the matrix, but now we're going to, in chapter 11, we use a capital M. But we showed that we have a bilinear form, quadratic form. I should say quadratic form here. A bilinear form is similar. You have this matrix, but you allow for two different vectors. That's a bilinear form. The proper term here is quadratic form. Okay, Q dot transpose. we have the so-called mass matrix. Okay, there you have it. You see the same structure. And so this is now going into chapter 11. This is the big picture for us. We will be using matrices. We're especially interested in these quadratic forms. Okay. If you're near an equilibrium, it's this term here, which is very important to you. First order derivatives are zero. So a Taylor series expansion of the potential about the equilibrium, well, first of all, you have an uninteresting constant. All the first order terms are vanishing. And then here you have all the second order terms. These are the second order terms. So this matrix is important to us. It describes the potential energy of a system near an equilibrium. Okay. And we understand that there's now a matrix involved. This is a result we had earlier. There was a time where we used a capital A. Earlier in the course, we called this thing capital A. In chapter 11, we like to call it the mass matrix. Okay, so we're going to make some remarks on matrix multiplication and how do you diagonalize matrices. Okay, I want to talk about this because if you've had quantum mechanics, you have probably heard that if you have two operators that do not commute, you cannot simultaneously diagonalize them, right? And yet, there is an appendix in our book, okay, where Taylor talks about simultaneously diagonalizing two matrices. So we're going to clarify that. The short answer is your quantum mechanics statement was in this interpretation of matrices. If you have two operators that do not commute, then you cannot simultaneously diagonalize them. Taylor's statement about simultaneous diagonalization has to do with quadratic forms. Okay, we have a question in the chat window here. Okay. Oh yeah, explain what Q and K are physically. A great question. So the question is, what are the Q and the K physically? All right, so the Q's are generalized coordinates. All right, so these are generalized coordinates. And we are using Lagrangian mechanics. Okay, so yeah, great question. Let's just remind ourselves, if you're doing Lagrangian mechanics and you have some system, the question is how many degrees of freedom? So we're going to have degrees of freedom, DOF, right? Degrees of freedom. This is the number of degrees of freedom. Okay, so we have n degrees of freedom. And so we'll look at some examples. Let's look at an example here. Suppose you have a railroad. Okay, so here's this railroad, and here are some tracks. Okay, so we'll turn back time to the good old days when we played with these locomotives on their train tracks. Okay, so here's a railroad, and we're going to attach some springs, okay? Remember, if there's a rigid wall, we like to diagram that like this. So here's a rigid wall, and here's another rigid wall. Okay, so now suppose we have some springs. Okay, so here's a spring and the spring constant is K1. That's a lowercase k. I'm going to emphasize that's a lowercase k. Here's a spring constant, this is K2. And here's a spring constant. So we're having a lot of fun building this thing. That's K3. Let me really emphasize it. Yep, we get to put together the railroad cars and the springs, mass M1. Okay, so this is an example where you have 2 degrees of freedom, right? We're assuming a one-dimensional railroad, and then the position of this relative to equilibrium okay, so we'll have x1 be the position of that railroad car relative to equilibrium, and for this one, x2. Okay. So for this problem, we have 2 degrees of freedom, little n equals 2. Okay. We could have called this Q1, and we could have called this Q2, but often when we solve actual problems, it's helpful to use a symbol that reminds you. And the symbol X is nice here because we think of a one-dimensional x-axis. Okay, so we could have called this Q1, and we could have called this Q2. But think of all the angles you've worked with and things like that. Sometimes if you have an angle, it's nice to call it theta or phi. It helps to clarify that, etc. So when we speak in great generality, we say Q sub I for generalized coordinates, and then we have this. So the other portion of the question is, what's K? So K, we're going to do a Taylor series expansion. Okay. So quite generally, we know the crucial concepts here. If you have the Q's, you can write the potential energy all right, and these are amongst our foundation concepts. Remember the classical state versus the classical configuration. The generalized coordinates tell you the classical configuration. So if you have these numbers, you have the classical configuration. The classical state of the system is determined by the Q variables and the Q dots. Right? Notice the potential energy is a function of the classical configuration. It's a function of the Q's. It is not a function of the Q's dots. So we do a Taylor series expansion. Okay, so what we're going to do is look at this function. This is the potential energy of a system. The system has many degrees of freedom. We have a function here, some formula that tells us the potential energy. That's a scalar. And if you have an equilibrium, then you know at the equilibrium, all of these partial derivatives, the first derivatives are 0. Those are those generalized forces, right? So I mean, it's part of the generalized force. So for what we're doing here, we're going to have the first derivatives vanish, the second derivatives. So the K matrix here, collection of second derivatives, and I'll put this here, second derivatives of U, and that's a function Q1 up to Qn. I better use a different color. It's getting a little crowded. I'm going to use a different color here. Okay, so I drew that in red ink. I understand the red is hard to see, so if I make it wider, then it's easier to see. And why did I do that? Because it was yet another arrowhead. There's already a lot of arrowheads, notice the double-headed arrow, it can be a little worrisome, right? So another arrow could make it even more worrisome and bewildering and overwhelming. So different colors sure help to alleviate that. Yeah, so this is a remark. We will talk about this K some more. Basically, it's a collection of second derivatives. This is a function of variables Q1 through Qn. So the second derivatives naturally can be arranged in a square matrix. Okay, so let's talk about this system here. We would like to understand this, and we would like to arrive at an eigenvalue problem. This system will have so-called normal modes. Those are modes where everything in the system is oscillating with the same frequency, and that's going to be an eigenfrequency. The general solution will be a sum of normal modes. Okay, so what you can do is write out the equations of motion for this system. For example, you can work out the total force. I should say total horizontal force. The vertical forces cancel. Gravity pulling down, the railroad tracks pushing back up, right? So the total force okay, this is a fun one. If we, there's certain remarks to be made about the rest length of the spring, but we're going to just skip those linear offsets. We got a minus K1, X1. That's the restoring force pulling it back towards the left wall. And then we got the K2. And the crucial thing here is an X2 minus X1. Okay. So you can go through this calculation. You do a similar remark for F2 and the force on particle number 2. And you arrive at two equations. These are the equations of motion, right? Equations of motion are differential equations which we must solve. So we have M1 X1 double dot is a good old Newton's second law equaling minus, we got the K1 plus K2 X1 plus K2 X2. We're getting a system, a coupled system of differential equations. The equation for M2. All right. We got the K2 X1. Again, that's telling you it's helpful to have three different springs here so you can identify these terms quickly. This is the force on that mass number 2 coming from an excursion here, holding that one fixed. Okay, and then we got the minus sign. K2 plus K3 X2. Okay, so again, this is an exercise where we write out the differential equations, and let's observe that you can write this using matrices. Okay, so at this point, we're going to introduce the K matrix as a spring constant matrix. Later, we're going to perceive the K matrix very generally coming from second derivatives of a potential energy. But let's observe in this analysis where we looked at forces, we can write this, and I'll use the double-headed arrow. There's the double-headed arrow. This can be written as a mass matrix times a vector double dot equaling minus a K matrix times a vector. Okay. So in our next meeting, we're going to investigate this structure further. But let the record show what we have done here is we've got a system of differential equations. The equations of motion here are a system, and they are coupled. You see both X1 and X2 occur here on the right. We have a system of coupled differential equations. We can introduce matrices to write the equations like this. Now, the analysis here has been in terms of forces. We haven't directly talked about potential energy and differentiated it. What we're going to do later in the chapter is do this second order Taylor series expansion of the potential energy, and we're going to get a K matrix in that context. Okay, so that brings us to the 2 o'clock hour. I'm going to stop the recording and I'll stay here for questions.